Hello and welcome to the Screencast, where we're going to try to sketch the graph of a function that's defined in terms of an integral. So here's the setup. Over here in the top left corner I'm given a function called g of t, and this function is made out of two straight line segments. The plug-in variable here, the independent variable, is t, and let's assume that the grid that you see underneath this graph is 1 by 1 on 1 unit on a side of each of the squares that you see. So this is 1-to-1 ratios here. We're going to define a of x to equal the integral from 0 to x of g of t dt. A couple things to note about this function. First of all, the independent variable of the function that I want to graph is x, not t. That x shows up on the right-hand side in the function definition right here as the upper limit of integration. So what this function a is going to do is measure the area that is between the graph of g, the t-axis, 0 on the left, and a moving point x on the right. This a, in other words, it's called a. I'm calling it a because it really gives me an area that's being swept out as a moves from left to right. So another thing to note here too is that the relationship between a and g, there's another relationship that's given by the second fundamental theorem of calculus. Namely, I know that if I have a of x defined in this way, that if I take the derivative of a, that's going to be g of x. In other words, this integral function is an antiderivative for g. And another way to think about that is that g of t over here is actually the derivative of the function I want to graph. So this is now a problem that you've seen before back in Calculus 1. You're given the graph of the derivative of a. That's what g is. Throughout this example, remember that g, the graph you're given, is actually the derivative of a, the graph that you want. And so if I know the graph of the derivative, I should be able to answer some questions and come up with some information about the original. So let's set to work here. I have 4 things down here I know I can pull off this graph immediately, where the original function a is increasing and decreasing, and where the original function is concave up and concave down. So let's see about this. Where is a of x increasing? Well, back in Calculus 1, you learned that a function a is increasing when its first derivative is positive. The graph of g is the graph of the first derivative. Okay, so where is that first derivative positive? That would be on the interval from 0 to 2, and then over here on the interval from 6 to 7. So that's 2 places, 0 to 2, and then also from 6 to 7. Now likewise, where is a of x decreasing? Well, the graph of a function a is decreasing whenever its derivative is negative, and that's in this interior region right here from 2 over to 6. From 2 to 6. Notice too, this gives us some information about where the local extreme values of a are. A of x changes from increasing to decreasing at x equals 2, and so that means that x equals 2 is going to be a relative maximum on a. Likewise, a changes from decreasing to increasing here at 6, and so there's going to be a relative minimum on a at x equals 6. All this information is great for the purpose that I am putting this to, which is to finally graph a eventually. Let's talk about concavity as well, because concavity is super important for determining the shape of a graph. Where is a of x concave up? Well, let's keep in mind from Calculus 1 that a of x is concave up whenever a double prime, the second derivative, is positive. Now, when the second derivative is positive, it means that the first derivative is increasing. So where is the first derivative increasing? Well, the graph that I'm looking at here is the graph of the first derivative. That appears to be increasing from here to here. That's from 4 to 7. So a of x is concave up whenever a prime is an increasing function, and that's from 4 to 7. Now, likewise, where is a of x concave down? That's where a double prime, the second derivative, is negative, and that happens when a single prime, the first derivative, is decreasing, and that is from 0 to 4 right here. So it appears I'm going to have an inflection point at x equals 4. So I'm beginning to get a mental picture of what this function is going to look like. The thing that would make this really work well too is to start plotting some actual points on the graph, and we're going to do that on the next slide. So here's a copy of the graph of G. The graph of G that you see in the lower right here, I'm going to use to actually superimpose the graph of A, our final result, on top of it. Let's see if we can calculate some actual values of A here. I know the general shape of A, but I actually think I have enough information to find out some points that really lie on this graph here. So first of all, what is A of 0? Well, keep in mind that the definition of A is that it's the integral from 0 to x of g of t dt. Now the x is the thing that I'm plugging in over here. So I'm looking at the integral from 0 to 0 of g of t dt. One of the things you learn very early on about definite integrals is that if you integrate from a point to itself, then the result is going to be 0. So A of 0 is equal to 0 in this case. Now what about A of 1? Well, likewise, that's going to be the integral from 0 to 1 of g of t dt. Now, since this graph of G is made up of straight line segments, I can actually find out the value of the integral from 0 to 1 exactly by using a little bit of geometry. Now, the line over here has a slope of -3/2 because it starts at 3 right here and crosses the x-axis at 2 right here. So if I go over by 1, I'm going to drop by 3/2. This area that results, the area from 0 to 1, is going to be sort of trapezoidal in shape. Okay? And I can find out that area by using the formula for the area of a trapezoid. That is, I'll do this down here, that's going to be 1/2 times one of the bases, that's one of the, that's sticking straight up this time, that's 3 units long, plus the other base, which is 3/2 units long. I started at 3, and then I went over 1 and dropped by 3/2, so I end up at 3/2, times the height, which in this case is just going to be 1. All that computes out to be 9/4. So A of 1 is equal to 9/4 in this case. A of 2, let me just erase this stuff to get it out of the way. A of 2 can be computed similarly. A of 2 would be the area under the graph of G from 0 to 2. That's this triangle right here, and that's very easy to calculate. That's a triangle with a base of 2 and a height of 3, and so the area, A of 2, is precisely equal to 3. I'll go ahead and write it out to remind ourselves. This is the integral from 0 to 2 of g of t dt. That integral is an area, and since this is a geometrically nice region, I can just calculate it out to be 3. So now I have 3 points that lie on this graph. I'd like you to pause the video for a minute or two and go over here and calculate these 4 values of A. A of 3, A of 4, we'll skip A of 5, do A of 6, and A of 7. So pause the video, go off with a piece of paper and work out the integrals, and come back, unpause when you're ready to proceed. Okay, so you've unpaused, that means you're ready to proceed. So let's think about these areas we have here. Now A of 3 is going to be a little bit different because I am now moving into the negative zone over here, and A of 3 should be about like this. The thing to notice here is I don't have to do a lot of calculation because the area from 1 to 2 is going to be equal to the area from 2 to 3. Except one's going to be a positive value and the other is going to be a negative value. Those negative and positive areas cancel each other out, and so I'm really back to whatever I calculated for A of 1. That's going to be 9/4 again. Now likewise, if I look at the area from, or the function of A of 4, that's going to be the area from 0 to 4. I'll highlight that. That's from all of this triangle plus all of this triangle. Okay. Now that's 2 equal areas, one above the x-axis, one below the axis, and so that area is going to come out to be precisely 0. I'm going to keep it my black here, and that's precisely 0. So the area from 0 to 4, again, that's the integral from 0 to 4 of g of t dt. Now we're skipping A of 5 and going straight to A of 6. A of 6 would be the area from, that's technically it's the integral from 0 to 6 of g of t dt. Now I know that the integral from 0 to 4 is just 0, so all I really need to do is calculate the integral from 2 to 6. 6 is where this just pokes up under the, or contacts the t-axis here. So that's a triangle that goes from 4 to 6, so it has a base of 2, and goes down to -3. So a base of 2 a height of negative 3, that must be an area total of negative 3. And then finally, at the integral from a of 7 would be the integral from 0 to 7 of g of t dt. Now that's the integral from 0 to 6, which is negative 3, plus this little tiny bit of area that goes from 6 to 7. That is just a single, that goes from, has a base of 1 and a height of 2, so that's an area of 1. And so negative 3, which is the area all the way from 0 to 6, plus that 1 unit of area is going to give me negative 2. Okay, so now I have 7 points that I've calculated using geometry here that definitely fit on this curve. So I know that we go through the origin. Then at 1, I'm at 9/4, so I'm around right here, 9/4, just a little bit higher than 2. Then I max out here at 2. We said we're going to have a maximum. I'm going to max out at 3 right there. And then at 3, I'm going to be back at 9/4. At 4, I'm all the way down at 0. At 6, which is over here, I'm going to be at negative 3. And then I'm back up to negative 2 at 7. So let's see if I can connect the dots here. That goes up, maxes out at 2, which is what we said. We said that A should have a local maximum at 2. Bottoms out here at 6, and we said that was going to happen as well. My function has a local minimum at 6, and then ends up right here. So this picture right here is A of x, as best as we can construct it, using the fact that g of t is A's derivative. So that's it for this example. Thanks for watching.